Lev, and also Zlatko for inviting me in this very nice conference. I'm really enjoying it. And also this is my first time to Brazil and this center, so it's really, really nice. Yeah, thank you very much. Okay, so today I will talk about MBL problem, at least from the Foxpress perspective, and I will let you know what we think about it. But before I start, let me also thank my collaborator, in particular Ishita Modak. She is a PhD student at IIT Bombay, and also Ferdinand Evers from University of Regensburg, who is my long-term collaborator. Okay, so let me directly start what we think and what is the thing that I'm going to talk about right now. So more specifically, I'm going to talk about a single model, more or less. It's a Heisenberg model in the SU2 symmetric point and with a disorder which is in the random field disorder. Okay. So what you see here is actually a scenario when interaction is 1, and this is a dynamical phase diagram where without any disorder, so in this direction the disorder is increasing. So without any disorder, it's an SU2 symmetry, so you get a KPZ type of scaling, which is very understood well now. And with increasing disorder, what we observe mostly is that there is a broad regime of disorder where it is thermalizing. Okay. We cannot pinpoint where exactly this stops, but there is a regime which is beyond the regime which is previously thought to be a transition point. So in this limit, in this model, particularly around at interaction 1, W3.5 was a celebrated number. Probably all of you could remember this number. Around that number, it was thought to be the transition between an ergodic regime to a localized regime. And at least we don't see that, and I think many of us do not believe that 3.5 is the true transition. Okay, so that's more or less what I'm going to talk about, but mostly what I will talk about is how the system is thermalizing, and try to give you a qualitative idea of how it is happening. Good. So in order to do that, this is my one slide introduction to the MBL. It will be introduced by Antonello next week, but still this is how things started. So more or less 20 years back, so these are the two seminal work, Basko, Leinert, Schuller, and Gorny Polyakov Marlin. They kind of asked the following question: what happened to a scenario when you have an Anderson insulator and electron-electron interaction is present? Okay, and they think about conductivity. So it's a conductivity at finite temperature, but now you know that we are thinking about a closed system. Therefore, temperature should be replaced by the energy density. So this is a finite temperature conductivity as a function of temperature. At very high temperature, you expect a Drude limit, elastic scattering, many elastic scattering will give you that. However, the whole point is that there is a finite TC, or in energy density language, there is a mobility edge. Okay, so there is energy density beyond which, strictly speaking, and that's the strict definition of the insulator that these two papers at least took, that sigma of T will be strictly 0. Not small or anything. Small has a meaning, separate meaning, but it will be strictly 0. So that's how they concretized the problem. At least that's how things started 20 years back. But now we are into 20 years, understood many things. In particular, the problem has been recasted in problem of thermalization. And as Lev also pointed out about ETH, so this phase that you see over here supposed to violate ETH. Okay, so that's number one thing. And then there are many other things that tells us that this is an MBL phase. So for instance, the ADL or entanglement of an eigenstate, you would expect some emergent local integrals of motion, LIOMs. If you start from a product state, do a quench, you would expect an entanglement growth, which will be logarithmically slow, and so on and so forth. And people have worked for 20 years now. There are many reviews. I pointed out this one by Piotr, who is over here, and also Lev, Antonello, and everybody, where kind of they told us what had happened in the last 20 years or so. Okay, so that's kind of the one slide introduction to MBL. But the question is essentially what is the reason for thermalization, and why there are so many noise about whether the MBL phase will be stable or not. So one of the things that I would like to start with is the mechanism of avalanche. Again, many of us here would know. The idea is very simple. So we are thinking about a disordered system. All the spins are localized. But in a disordered system, you would expect, even though it is rare, a region which could act as an ergodic bath or a bubble. Yeah? So that part is thermalizing, except not the rest of it. But the idea is if you can do that this rate thing will eat up the nearest neighbor spins, slowly it will increase and slowly it will thermalize the whole of the thing, but not always. There are certain regime where it will and certain not. And one can do a simple kind of a golden rule type of calculation. So for instance, one try to see what is the matrix element between this edge of the spin to the rest of the spin. And as they are localized, you expect that this matrix element will be exponentially suppressed. And what one needs to calculate, what one needs to compare this matrix element is with the level spacing of the ergodic bubble. Yeah? So as long as the matrix element is strong enough, or in some sense it doesn't see the discreteness of the spectrum, what you expect that this will be strong to delocalize or let's say thermalize the next spin and eventually the next and the next and the next. Yeah? And one can find out a criteria for that. So the criteria is that one needs to have a correlation length, which is this xi, bigger than 1 over log 2 for this thermalization process to take place. Yeah? Once that happens, the system is supposed to thermalize eventually. So even if there is a localized phase and if you find ergodic bubble, the idea is that this phase will not be stabilized. Yeah? So this type of event will destabilize the MBL phase. Now it's very difficult to see it actually in real microscopic, but there are many attempts and I show 3 things. So one of the attempt is actually you start with an Anderson insulating state, this is a spin, and then you add an ergodic bubble over here. So it's a GOE bubble, and that has that is an RMT, random matrix theory, and you couple it progressively with all the spins over here. So that's one way of saying that, okay, my system already started the avalanche process. Yeah? So already I have the ergodicity inbuilt into the system, and the question is whether that ergodic bubble thermalizes the whole spin or not, whole spin chain or not. That's one way of thinking. So this is another, this is called SAN model. Again, Lev worked a lot on it. So the idea is, again, you have a GOE bath, and then all these spins are individual spins, but they're coupled with their coupling with an interaction strength, which depends on the length of the direction. And the third is essentially an experiment. So this experiment is over here. So this is an optical lattice experiment in a periodic potential, quasi-periodic potential. And then they did the same thing. Yeah. So the left-hand side is essentially an ergodic bubble. The right-hand side is essentially a Anderson insulating chain. And the question is again similar, that whether that ergodic part will eventually delocalize the right-hand side. And all of these things essentially answer yes. Yeah? So there is no surprise, more or less. Whether you do it in different ways, most of the time it says that, okay, it will thermalize. That's the idea. And then that kind of gave a suggestion that, okay, maybe this is the method with which MBL will be destabilized. I also would like to mention that there is other setup. So essentially this is by Dries and co-workers. So where they measure the following things. So they have the same spin chain, but then you have a local bath. Yeah, it's a Lindbladian bath. It's a particle bath, and then you drive the system with that local bath. And again, the question is what is the avalanche instability? Where the avalanche instability? How the avalanche instability behaves with system size? Here, in particular, plotted the rescaled relaxation time. And what you see over here for different system size, the avalanche instability is essentially the crossing between 2 lines, and it keeps on moving with higher disorder value. And that kind of gives a natural interpretation that indeed it will go to infinity, as in there is no transition at finite disorder. But at the same time, there is also this work. So this is a work by Angelo Russomano group. What they did is a similar setup, except instead of a particle bath, they have a heat bath now. Okay, so it's a local heat bath, and then they calculate again the time scale that it will take for the energy to transfer from one end to the another end. Yeah, and they found that this is logarithmically slow. More or less, they eventually could find a time scale also it takes for the system to delocalize, and that is exponential in system size and disorder. And that kind of allowed them to find a critical disorder strength, where they say that avalanche will essentially stabilize MBL. Okay, so that's kind of an opposite work. So this is this PRB from last year. And in that sense, I would say that this, at least, is not yet conclusive, which one will win at the end. Okay, so that's kind of a rough avalanche story, which is happening for several years now. Now, there is another method, which is called resonance, which would allow you to drive delocalization. And the simplest way to understand resonance, I think, is going back to Mott. So that's kind of the 68 paper by Mott. And what he was considering essentially is an Anderson insulator at finite temperature. Okay, so this is what is plotted over here is an energy, single particle energy, so non-interacting system, as a function of system sizes. Yeah, so you know that Anderson insulator, in one dimension, all of the states are localized. And this is a nice way to see that all the states, so this is essentially the local density of states, again has been introduced to you yesterday. So this is the local density of states in this coordinate system, energy and position. So all of them, as you can see, are localized within some localization length over here and at some energy. Fine. So that's the non-interacting Anderson picture. Now, what Mott's argument was the following, that if I bring this system in the presence of a bath, which is a finite temperature bath, and if I find this type of states where you look, these states and these states, they're far away in space, but close in energy, single particle energy. And if you wait long enough, at finite temperature, there will be some phonon which will have energy which will compensate these two energies. Yeah, so the difference in energy. And that's resonance. Once these two states comes in resonance, you will expect that particle to move from here to there through variable range hopping. Yeah, and that gives transport. It is exponentially small in 1 over temperature. So that's an exact formula from Mott. So that's a sigma, again, going back to this conductivity at finite temperature. Some prefactor is there. That's the kind of the Drude prefactor. But then there is this exponentially small factor, depends on dimensionality and this delta of xi, which is the single particle level spacing. No, please go ahead. Yeah.
This is possible. I can understand this if, matter is coupled to photon, like in a cavity, which brings a non-local interaction. Hence, you can couple different parts of the system. But how is this possible with a phonon?
And phonon also globally coupled to all the system. Means it's that you think of the system, means all the electrons are coupled to the phonons.
It's like a test site. Like your phonon also has like a site index. That is different, for example, with the photon coupling. Photon will be
it's not a single process.
okay.
Yeah.
It's variable range hopping.
Yeah, okay, sorry. Yeah. So it's not that the particle move from here to there. There are virtual processes.
Far away with that rate. But the processes are local on the scale of the localization.
Yes.
Many of them.
Yes.
By borrowing energies from the phone. When you optimize over the range, that's variable range.
Yes. Yeah, so there are virtual processes if you wish. So it's not that one step it goes from here to there. That's if that helps. Good. So in the case of many body, you obviously the single particle energy densities are not the right quantity. You have to think about many body energy density, and the space has to be replaced by the spin flips. How many spin flips they are away to many body eigenstates. But again, they can come in resonance and can drive delocalization over the entire energy spectrum. Yeah? So that's the idea of resonance. And now, again, this is one process with which system can delocalize, and that was initially a reason why people thought there is no finite temperature insulator. Yeah? So there is no, in particular, and that's also the MBL got so much height in a sense that you are finding an insulator which is finite temperature or finite energy density. Good. So these are the two things I wanted to mention, two mechanisms. Okay, now let me come to this enigma. So what is about this 3.5? So as I told you that initially we thought that the transition is around 3.5, and I wanted to revisit it and wanted to tell you what's happening over there as well. Okay, so what has been shown over here is a non-interacting localization length. Yeah, so you do a transfer matrix calculation of a 1D Anderson model, and you will find that the localization length depends on disorder. At small disorder is proportional to 1 over W square, but then there is something happening over here. And if you look at it carefully, it's plotted over the same W, such that I can compare it with the interacting case. And what you see around 3 to 4, this localization length becomes order 1 and becomes even smaller than the unity, means lattice spacing. Why I show that? To tell you that to get an idea that this 3.5 is not a small disorder, it's not a weak disorder physics that we are looking at. So it's already extremely strong such that the local orbitals or the single particle orbitals are localized within a single lattice point. Yeah, and that's a strong disorder. Even for system size 20, 24 that we are doing, it's a strong disorder. Good, so that's one thing. And definitely I want to flash this figure, which is the interacting figure. Yeah, what is plotted here is the energy density as a function of disorder strength in the same unit. This is a paper actually 10 years back from David Lewis and Toulouse group. And what they showed, they had calculated, I don't know, several different observable entanglement entropy, participation entropy, R statistics, fluctuation, many things. And each and every of these things kind of has shown this mobility edge. Mobility edge means that there is this kind of shape. It's not a straight line. And if you look at 0.5, which is the infinite temperature, you will see that the transition happening around that number only. It's very weird. It's just probably a coincidence. I don't know, but I just wanted to mention that happens over here. However, again, recent years, we have been watching, observing that the WC, which is quoted to be around 3.5, 3.8, is a function of system size. Now, if it is a function of system size and keeps on going, then this phase doesn't exist, whatever the mechanism is. Whether it stops or not, I think that's a big question, and I don't know what is the final answer yet. Okay, so that's another aspect of the 3.5. Now, I also want to mention, so all of these quantities that has been measured over here is a eigenstate properties, the single eigenstate properties as compared to the ETH type of perspective. If you look at dynamics, so let me just look at the dynamics around that number again. So what we are doing again, just to concretize, this is the model. It's written in a fermion language, but Jordan Wigner is a XXZ model. Spinless fermion Hubbard, unit interaction, hopping is unity, and only thing that matters is the disorder, which is on-site disorder, distributed in uniformly, minus W to plus W. And what I will monitor is actually the density correlator. So it's a two-space, two-time correlation function. So what it measures is essentially you have the chain, and then you create a density excitation. Yeah, if you create a density excitation, you want to know how it propagates. Mostly the width of the propagation that I am interested in. And if you calculate this quantity, the width of the propagation is the second moment actually. It grows with time with some exponent beta. If it is a diffusive system, this beta will be half. Okay, and let's monitor what happens around that. So I'm going to show you essentially the beta itself. So it's a log derivative of the delta x divided by the log of t, plotted as a function of how big the size of this web packet is, normalized with respect to single particle localization length. Okay, so time has been reparameterized by the distance itself. Yeah.
Constant of time
No, this is what is showing. Beta is not a constant of time.
Well, this is
Precisely the time. This is precisely the time. Yeah. Beta, exactly. This is what I wanted to mention, that these are the three data. So below 3.5, above 3.5, and around 3.5. And what you see is the following. So the beta, first of all, first thing to note, is never converged. Yeah, it's keep on increasing with system size, at least up to 30 system size we have checked. Never I see a converged exponent. So this is system size small to large, and you growing, and this is half. Yeah, that above line is half. So we are below the diffusion limit for sure, but it's also not converging. But what I wanted to show you that this below here and above here, the slope with which it is approaching half is different. Yeah, so here is a positive slope, whereas here is almost flat, and probably you can read off our exponent. Whereas here is a negative slope, but again, if you look at carefully with increasing system size, it's keep on coming up. Yeah, so even at 5.5, we do not see that it is 0. That's what I wanted to say. And that kind of tells us that there is transport, slow, but transport. Good, so that's an infinite temperature correlation function. This we cannot measure in experiment, at least in the modern day experiment that deals with MBL. So what it can measure is quench. Okay. This is another aspect that I want to mention, and then I'll come to the main thing. What modern day experiment can measure is essentially a quench, starting from a null state. Yeah, so you start with an up-down state. You calculate how much imbalance is left after the time evolution. And this is what has been shown over here. So this is the imbalance plotted as a function of time. Below the trend, again, this 3.5, okay, for 10 typical samples. Yeah, it's not averaged over anything. And what I wanted to show you that there is a huge sample to sample fluctuation. So for instance, if I just follow this blue, this yellow one, it goes to 0. Going to 0 implies that there is no memory, ETH is obeyed, this system is thermalized. Whereas up to this time, so by the way, this time is measured in the unit of the inverse hopping. Up to this time, what you can see clearly, there are samples which will be almost non-thermal.
What is the dimension of the system?
This is 24. So yeah, so what I wanted to mention that even at 1.5, below this controversial number 3.5, the sample to sample fluctuation is tremendous. It's mesoscopic fluctuations. We know it exists, but it's huge. But I also want to mention that the system, this imbalance is self-averaging quantity, short time, long time, no problem, but it's tricky. There is a re-entrant behavior. If you want, I can explain later. Good. With this, let me summarize what I have talked about. So there are several things. Yeah. So whether there is, so first of all, there is this type of phase diagram. Something is happening around 3.5. One cannot ignore that. Yeah. So there are avalanche, probably. There are resonances, definitely. There is slow dynamics across this value WC 3.5. And also I want to mention that there is a strong mesoscopic fluctuations at peak disorder. Okay, so that's where I think of this field, and that's from here I would like to tell you some bit of this kind of things from a Fock space perspective. What Fock space sees for all of this. Yeah, I'll not be able to answer all of it, but let me see. Okay, if there is no question, let me just go ahead. I need some definition. So again, I will think about quenches. Yeah, so quenches from a null state. That's the only thing I will do. So what I need is essentially, I am thinking about a basis, Fock space basis, which is the occupation basis or a computational basis as we wish, we do it. So it's 1001, this type of basis. Yeah? The energy of that basis states is essentially given by the diagonal part of the Hamiltonian. Okay? This is simple. Whereas the connectivity between these Fock space basis is given by the hopping amplitude, which is essentially for us is constant T. That's how the Fock space is constructed. Now, what I am interested in actually is the variance of the initial state. Okay, so that's the variance of the initial state. Psi nil is the initial state, and this delta shell, I will call it a potential energy shell. And again, the importance of variance has been discussed in the ETH context by Lev. But roughly speaking, that kind of gives the time scale of the observable, decay of the observable. Yeah, so in the ETH. And what I am interested in, of all those many-body Fock basis state, that is within this variance. Okay. If it is not clear, let me just give you an example. So this is kind of a 2D representation of the many-body Fock space. I start from the Snell state, which is over here, and all the states is arranged as a function of Hamming distance. So Hamming distance is nothing but one flip away, yeah, one tunneling away. So if you operate your H with that state, all of these states will appear, and so on and so forth. Yeah? So that's the increasing Hamming distance. I'll tell you more about it later.
The color.
Yeah, that's the next sentence. Next sentence. And yeah, so what is the color is the following. So first of all, along this direction, the increasing Hamming distance, y direction is arbitrary. There's no order in it. And what is this red compared to the gray is the following. All these red basis state or the Fock states are within that energy shell. That's it. Okay. Now, here is one typical example. Just to give you.
You leave some white spot like.
No, here, this is just arrangement, just to make it symmetric, but nothing, no significance, no significance. And by the way, this is a 2D projection anyway, so Fock state is obviously a very complicated one. Okay, so just about the scaling of this width. Yeah, so this has been discussed. The scaling of this shell, the width of this variance is essentially 1 over, goes as square root of L. And that can be understood from the fact that my Hamiltonian is nearest neighbor. There is no long range correlation in it. So this is short range correlation. You can factorize it and can quickly show that it grows at square root of L. And if you measure that with respect to the many body bandwidth, which grows with the linear size of the system. So this quantity, the delta shell divided by delta bandwidth, is a vanishing fraction, is a 1 over square root of L.
Bandwidth scale decreases with L.
global density states as a standard deviation scale, sort of most familiar. I know it's common to scale things in terms of L, but
Right.
the states that lie beyond the blue L and is from the mean are exponentially small in number.
That is true. So actually, that is what my next statement is, that within that shell, even though the system is increasing, but within that shell, yeah, that's the density of states. Within that shell, the number of states that increases with L is exponential. So even though it's polynomially going down, polynomially becoming small compared to the many-body thing, the number of states is not. Yeah. So that saves me. Okay. So that's the setup. Now the rest of the game is very simple. What I'm going to do, I'm going to look at this picture again and again and again for different system sizes, different samples, different disorder value. And I want to know what is going on. Good. So this is two samples. Again, two arbitrary samples. All I'm going to show in weak disorder, then I will go to the large disorder. So that's one sample where the number of red points is compared with the dimension of the system. And what you see is the 70% is covered. And what you quickly see, and I will try to correlate with the quantity which is imbalance. Yeah, so once it is around 70%, quickly it goes to 0. Whereas you see it's a very small number, 25. Again, same disorder, just the different sample. What you see is that the imbalance is finite and fluctuating. And if it is the case, if it is the story that, okay, there's just the density of states matters, this doesn't care.
So I will guess that the configuration like the left is way more abundant than the configurations like, because these are two different disorder realizations. It's not the case.
It's not the case. Yeah, there's a little bit more to it. Okay. Okay, exactly. So the point is that if it is the case that large goes to imbalance, small is a large imbalance, then we are done. Yeah, so then we don't have to think about it, but that's not the case. Let me give one example. So this is more than 25, is 35%. Imbalance is more than 0.2 if you have noticed it previously. Okay, so there are samples which are completely opposite, atypical. The question is, what am I missing? What am I missing is actually connectivity. So it's not enough to think about the density of states, but also you need to think about how the nail state is connected to the rest of it. And that's very important. Now here is the point. So it's a 70%, but what you see is the connectivity of these red points, and it's completely forming a big cluster over here. Yeah, once it forms such a big cluster, imbalance is very small.
Sorry, the graph is always the same. Here you are highlighting the connections that are between red.
Only red.
Okay.
Within
okay.
that,
you agree that the full graph remain always the same, but here you are
extremely careful. So everything is connected to everything.
Exactly. But
I'm
here
only monitoring within that variance window what is happening.
Okay.
Now you see that previous plot, the 35%, but large imbalance. And what is happening over here, you already see that the nail state, which is over here, is essentially connected to 3 other states. And then there is a big chunk of it over here. So that's the fragmentation. Now at this point, you might say, okay, this is just an artist impression, and I'll show you that's not the case. Yeah? In order to see it's not the case, what we need to see is actually the dynamics on the Fock space. Yeah? So this is the dynamics of that particular sample for different time. Yeah? And what I am plotting here is essentially the local density of states in the Fock space. Yeah, the amplitude, if you wish, yeah, mod psi square, normalized with the max. So this is the quantity that has been plotted. Okay. Now it's 35%, but still what you can notice that most of the amplitude is essentially staying in that cage. Yeah, so over here to up to 10 to the power 3 is there. It's not moving away from that point. And not only that, I also want to point out that there are resonances. So for instance, if you look at 239, 288, 380, you can almost see that the configuration is similar. Yeah. Same thing if you look at 255, 370, 123, the configuration is almost similar. You can identify it just qualitatively. That means that essentially the wave function is moving around. It's just doing that. The reflection of that in the imbalance is these oscillations. Please. No, it just comes out from the thing.
There are that big circle.
Oh, it's just what is the value of this mod psi square? That's it. Yeah, I didn't put the scale over here, but this sum over will be 1, just the normalization. So if I sum over all of it, it's just 1. And this means that it has the largest amplitude. That's it. Maybe very small because the number of Fock states is exponentially large. Okay, so again, if I just stop here, that's good, but that's not enough, as Dario also pointed out, that this block is, even though it looks fragmented, but eventually it will get connected because everything is connected to each other. And that you also see in imbalance. If you look at it, you will see that there are these oscillations, but then there is a slope, and that's the leakage. Okay, so it will be there, but eventually it will all get connected, and that gives information about why there is a slow dynamics.
What system size?
This one is, I don't know, 12 or something, just for the purpose, but I will show you larger system data. Okay, so that's kind of the interesting thing, and this is the correlation. So what has been plotted here is the saturation value of the imbalance. Yeah, for those size of the cluster, NC now is the connected cluster size. Okay, it's not the number of red dots, just the connected cluster which incorporates the null state, normalized with the dimension of the Hilbert space. And what you see this is in a log scale, that ergodicity would imply that the imbalance goes to 0, and a large imbalance would imply that those samples are not thermalizing. And the correlation is clear, it's just diagonal even. So this is system size 12, this is system size 20. What you see over here, that there is a long tail, and this is the strong fluctuation that I was mentioning to you, that there is a huge number of samples which shows large imbalance, small size of the cluster, and vice versa.
It's some solution variable is limit t to infinity. Numerically, it's 1000.
4000. It's 1.5, by the way. Disorder is 1.5. If it, so it saturates, let's say. But yeah, but I have data for 24, which I cannot do. So 12, 16, maybe 18, maybe, but then. Okay. Okay, so I hope that I tried to convince you two things. Yeah, so there are two things. One is there is an effect of density of states. How many red dots are there within this variance window? And that gives the fluctuation even at weak disorder. But once you go to larger and larger disorder, not only the number of red dots reduces, but also it fragments. Yeah, so these are the two effects kind of give rise to the fluctuation and around 3.5 this issue. Now this is about a couple of samples that I mentioned to you. But then obviously, what about average properties? Yeah, I need to tell you that this picture survives in thermodynamic limit, right? And here I would like to make a comment about this very nice work by David Stithodi and John Choka a couple of years back. They also considered something called a classical percolation on this many-body Fock space. The idea there was the following, in simple terms, that you consider what is the energy of these Fock states, nearby energies, and you compare with the T, the hopping amplitude. And if the difference is larger than T, you keep those two sides. If they are smaller than T, you throw away that connectivity. Okay, and that way you can also form a cluster and see certain aspects of MBL physics. But at least in our case, I think it is a bit different than what you guys have done. Yeah. So if maybe there is some connection, but we are yet to find those connections. Yes, yes, yes. Because it's a classical kind of thing. Okay, with this, let me tell you a little bit about the average property. So what I have been showing you is over now is the average size of the cluster as a function of disorder strength. Yeah, so again, average size of the connected cluster. And there is no dynamics, no diagonalization, nothing, just the size of the cluster and averaged over many, many samples. And what you see here, so going from 20 to 24, exactly a similar type of plot that you have seen previously with any quantities that we have looked at previously, whether it's a level spacing statistics, whether it's entanglement entropy, whether it's this and that, and so on and so forth, you see that. Yeah, but the interesting part is actually the variance. Okay, so again, if you look at the variance of this quantity, what you see that there is a peak, and exactly around between 3 to 4, the peak highlights itself. Yeah, so that's where the fragmentation is happening. Fluctuations are really large. Now, it turned out that this things moves, and this is exactly the point that I mentioned, that WC is a function of L in recent years, and this is that movement even seen in this average size of the connected cluster. It can be a small power law, can also be log. I don't want to claim very strongly over here, but it moves, and we do not see a sign of saturation as of now.
So yeah, what does it mean?
Yeah, it moves from around. No, I'm saying I'm not claiming anything. I'm just suggesting that it doesn't stop.
Soumya, how do you do without diagonalization, without...
Exactly. So I have a Hamiltonian, I have the nail state. Variance is just the overlap.
Ah, stupid. Yeah, sorry.
No diagonalization, nothing. And actually, my student didn't push it, but one should be able to go even larger. It's just counting. But it's still exponentially hard counting. Okay, but I think I wanted to end with a bit different idea. So now, instead of this looking at variance and mean separately, let's plot the variance and mean by each other, forgetting the disorder value. So all the disorder, all the system size I have plotted over here, and I need one quality, means kind of a heuristic parameter square root of L, and what I observe is there is a universal flow, universal curve. Yeah? And give me 2 minutes to read it out. Yeah? So I will tell you how to read this plot. I hope this is clear. Yeah? So it's essentially the previous two plots plotted in a one single plot. Now, you see over here the blue lines over here, and you need to just keep on monitoring pentagon, cross, circle. Yeah? So if you monitor the pentagon, cross, and circle, you will observe that at weak disorder, which is 1.5, this thing moves towards right. And that's good, because NC equals to N red means that I have a big, huge cluster on an average. Yeah? And that's like the no fragmentation limit. That's the limit when I have shown you that the saturation value of the imbalance is close to 0 as well. So that kind of, to me, is an ergodic fixed point. Okay, and it moves over here. And you can monitor again anywhere pentagon, cross, circle, pentagon, cross, circle. Yeah, so they are moving along that line. Now let's come here, localized fixed point. So if you now monitor this one again, pentagon, cross, circle, same color, that's W5.5, you will immediately say that, oh, there is interesting physics that it goes towards, seems like a 0, and 0 means extreme fragmentation, and that's my localized fixed point. Okay, but if I again stop here and go, you will immediately say, okay, good, I see MBL, I see this, but that's not the case, because you have to kind of monitor it a bit more carefully. Yeah, so again, the fact that there is no collapse over here is not accident. It's not noise either. There is a physics. And the physics you can see over here. So I zoomed in this direction, and what I show you, you see that the pentagon cross circle, pentagon cross circle, pentagon cross circle, pentagon cross circle are taking a U-turn. Okay, so it's kind of the similar thing. So up to some length scale, it feels that, oh, I should go towards the localized fixed point, but then it takes a U-turn and goes towards this universal plot. And if it flows to this universal line, it implies that all of them will go towards that thermalized fixed point, and everything will be thermal. Good. So that's kind of the interesting part in this part of the data. But then again, you see that over here, this pink pentagon cross circle doesn't show that U-turn yet. Yeah. And then you would say, okay, no, then this is fine. But what you have to monitor is that it is preparing to U-turn. How? The how is that the distance between 2 points are decreasing. And that has to be the case. Yeah. If that happens, then only it will stop and move up. Because whenever in this line, they are equally distant, you see. And whenever it's trying to go U-turn, it's reducing the distance between the points, stops it, and moves up. Okay. So that's the beauty of this plot. So it tells me that even though it doesn't yet did a U-turn, but it will. Now, which branch it will grow, I don't know. Anyway, so with this, I think I have taken my time. Yeah, Zoom. So I want to finish with this idea, that this conclusion that the common expectation is that dephasing usually leads to thermalization. That's MOT. I don't need another mechanism for thermalization, I thought. So to me is a much more open question, what is the mechanism that is responsible for localization? Because maybe Anto will tell us next class that in order to do or see localization is much harder problem. Actually, you need this locator expansion. You need all the diagrams to be summed very cleverly in order to see localization. That's much more difficult than saying that, okay, there is a delocalization. That's perturbative. We saw it yesterday. So that to me is a more interesting question than saying that, okay, there is this mechanism, that thermalizes it. Anyway, that's my perspective. And what I would say is that fragmentation of potential energy cell is a relevant concept, at least to understand this transient dynamics, this slow dynamics, as well as localization in these intermediate system sizes. With this, I'd like to thank again the organizer and to all of you for listening.
Thanks a lot. More questions?
So this issue, when you observe scaling of these things, that there is a minimum and then goes back up. You actually see it very well also in the numerics on the Anderson model on the regular random graph.
Yes.
Okay. And this is actually, I will tell you the third lecture, not next one, but after that. But this doesn't mean that there is no transition.
No, I'm not saying.
Okay, I'm just saying that it means that if the transition occurs, it's of a two-parameter scaling kind of transition. It's not a single parameter scaling.
Right.
So it's more similar to Kosterlitz-Towles than to the Ising model in 3D.
I see.
Okay.
Yeah.
So you can see, because I mean there are all these curves, but then at a certain point, one of these curves just intercepts the origin, and all the other one they go. You need another axis actually. They would go on they would stop on the lower part of the.
I see.
Yeah,
It can happen.
So it's interesting. It tells you that, you know, if you try to do data collapse within a critical exponent nu of this thing, then they don't collapse.
Yeah.
Or if they collapse, they give you nu, which make no sense.
Yeah.
But there is, if you analyze it properly, the RG flow near there, you can get the transition. It will be higher than 5.5, but I think at this point we know.
Yeah. Okay.
Yeah. So here you're showing variance, right? Which is so for a given W and L, you have one number.
Yes.
So is it also possible for every realization to have plot that then, but then it's not an arc, right? It's something similar that you showed initially, right?
Yeah, that is difficult because I tell you why doing the whole thing is a bit difficulty, because, you know, for weak disorder, I can show you the saturation. For larger and larger disorder, we always see that there is a weak flow towards zero. There is no saturation. So what to say saturation is a bit of an issue there. Therefore, such a nice correlation is absent at high disorder. That doesn't mean that it's not there. It's just that it's difficult to see. With increasing system size, we see that coming up, but it's not clear yet. Yeah, so doing this in that form will be a bit. We have something, but it's we have a collapse. I'll tell you later. I'll show you. All the data actually collapse, but one has to be careful.
More questions? Okay, I go with one and then we go. Here, let's say how can I say? The non-localization is due to the fact that this leakage is too strong. Yeah, let's say.
Eventually, it's just the time scale.
Exactly.
So it's
so in some sense
extensively connected.
Could we say that you will need, let's say, MBL as it is formulated creates the clusters and the small clusters, but then you will need an extra mechanism that reduce the leakage.
Precisely. That's why I'm saying that the localization is a difficult problem.
Okay.
So for me, the localization would imply that actually there is zero. That's my next point. So essentially what it means is that there's only one state.
Yeah.
That's it.
No, but in principle you could have more than one, but should stay stay there.
Difficult.
So okay.
Difficult problem. Yeah.
Okay.
We don't see that.
In guessing that, I mean, if if this was to go to zero, it's all right, I've got a loud voice. If this was to go to, if this was to go to zero, it could go in a way that grows with L, you know, it could be. It's not that you will end up with Anderson localization in
No,
Fock
no, no,
space. You
no.
will generically end up with something that's multifractal like in Fock space. Right?
Yes.
Okay, fine.
Absolutely.
And you
That
can't
I
tell the
can't-
difference when you look at that kind of block, right?
Yeah, that
Couldn't
I
tell the
cannot.
difference. All you know is
No,
it's
but
going.
in the Anderson localized case, if I just plot this, there is nothing like variance of this because none of them are connected in my
On the
basis.
Fock space graph, you're never going to end up with a state that is just localized on an order one number of
Sure,
states.
sure.
Okay,
Sure,
that's
sure.
that's
Sure,
taking it away, which I think
Yeah.
Good.
Okay.
No, wait. More than that? No. Okay, so let's take.
Thank you.